Okay, everyone. Thank you all for joining. It's Ophir Maor here from HPC Advisory Council. And we're happy to start our first guest lecture. We have Geoffroy Vallee from Nvidia. Geoffroy, you're a presenter, and Geoffroy is going to talk about the coding challenge, about the tool he was developing. We are going to use this tool to try to collect, to profile all-to-all-V, MPI all-to-all-V, focusing on that. Geoffroy will walk through the tool. I will go through the challenges, and we'll have some open questions in the end.
Thank you. Yes, my name is Geoffroy Vallee. So it's been a tool that I started to develop with some other people. Sorry. About a year ago, really. And that was really a tool. The goal was really to investigate some applications we were dealing with, and that did not give us the performance we were looking for. So it's clearly not a product even today. It's really a tool for investigating things, try to understand the behavior of applications, and try to, really understand what is going on. So again, it's not a tool, which means it's not super finalized. There is not tons of documentation. I did my best to write as much documentation as possible, but it's clearly not a product. It's an open source project, so everybody is welcome to contribute. And we make it evolve as our needs are changing and as we get more contributions from other people. So some things that you need to keep in mind. So I don't know what is your background, all of you, but this is based on the MPI standard. So if you don't know very well what is the MPI standard, I strongly advise you to have a look at the standard itself. It's a very standard, a very well-known standard for the HPC community. So it's really the standard we use most of the time to do parallel computing. And everything I will talk about today, and even your project, it's actually focusing on one specific operation from the standard. It's all-to-all-V. So all-to-all-V is what it means. It's a communication pattern where all the ranks in the communicator, and I know I'm using some technical terms here that would be obscure for you if you don't know MPI, but all the entities involved in the communication are communicating with every other all-to-all, every other entities in the communication, involved in the communication. We have some other operations that are under development, but they're not fully supported yet in the repository, and I won't talk about that here today. So again, and I want to make that very clear, the goal here of that tool is really to gather data to understand performance bottlenecks, to understand why in many cases when applications are using all-to-all-V, we don't end up with the performance we are expecting. And we try to do that even if we don't have access to the source code of the application. So that's really some of the motivation why we developed this tool and why we are going in that direction. And I think it's very important for you to understand that those are the motivation, and we have to keep it in mind every time we do development on that tool. One of the constraints is that we need to be able to execute very easily that provider on any execution platform. It's not unusual to have people who contact us for help, and we have to use that provider on their system, not our system, and we have very limited access to it. So that's, again, something that you have to keep in mind, and that's some of the motivation of why the tool is implemented as it is today. Another very important point is what is the target scale for that tool? So we want to support a large count of ranks. So again, the number of entities that are involved in the communication within the application, and a very large number of nodes. And I think I will give a little more details about that later. And the tool is really how to gather the trace, but also all the tool chain necessary to analyze the data. Because if you only gather the trace, it's not quite enough. You don't have anything really readable to understand why you have these performance bottlenecks you are trying to investigate. And I put a link to the Git repository. I don't know if you would have a copy of the slides, but I think it would be good for you to have a copy of the slides so you can have the link and don't have to write
Yes,
it down.
I'll just mention first that we'll have the copy of the slides, and I'm also recording it just for a future, if you want to go back to it, or some people didn't show up. So, okay.
Perfect, thank you. So just an overview of the architecture, again, is to give you a feel of what the tool is and what you can expect. So as I said, there is two separate pieces. The first one is how to create the trace itself, the profile, and that piece is in C. Please, can you mute yourself if you're not talking? We have a lot of background noise. Thank you. So the profiler itself is in C. It's using what is called PMPI. That's actually an interface on top of MPI specifically designed to implement tools. So that's a standard. All that code is in the source directory, so you can look it up, you know where it is. And it really creates a set of shared libraries. So for your project, you would have to only use the default set of libraries. There is a lot of complexity in the tool to be able to customize what the shared libraries are doing. You don't have to worry about that. I don't think you will. But that's also something to keep in mind. It can generate a lot of stuff. If you dig up into the code, you will see that there is a lot of weird code to be able to generate many different things, a lot of ways to generate different behavior for these shared libraries. But again, you should not have to worry about it. And the second part is really the postmortem analysis tool. So this is in Golang. If you don't know Golang, it should be fine if you know CFC. It's very similar. It's actually easier. You don't have the concept of pointers. Pointers are hidden away within the language, and it's in the tools directory. And that's really what we have, what I developed over time to go through the profile, extract statistics, data, everything we need to understand the performance bottlenecks I was referring to. And that tool, there is two aspects, but ultimately the one way to think about is it's a set of commands that you can run just to perform very specific steps on the data set and do the postmortem analysis. I strongly advise everybody to look at the README file. It has much more information than this presentation. Here, I just go quickly over the overview and some specific points. The README file has a lot of details about how to use it, how to install it, and everything. I'm sure there is a lot of space for improvement. And if there is things you don't understand, there is a Slack channel and free to ask questions. We will do our best to answer in a timely manner. So I said there is a lot of command for the postmortem analysis, and here I wanted to give you a very specific idea of what it means. So first of all, I try to do my best to follow the best practices regarding software engineering, which means you have one command to compile everything. It's make, and it will actually compile both the share libraries to create the profile and also the tools. So you don't have to worry about understanding all the internal mechanics to compile everything. You have one command that does it all. To run the profiler, so to create that profile, once you have your application, how do you get the profile? And then you can, to later on, do the postmortem analysis. So it's the MPI run command, which is standard, and you just have to add the -x AD preload and the link, the path to the library, and that will do magic. It will do everything for you. That example is assuming you have a specific implementation of MPI, and I think that's actually an assumption that would be made for your project. But again, if there is questions about those technical aspects, we can see later. And for the postmortem analysis, so here, and I will talk a little bit more about it in a few slides, that's the main command to run the profiling, the postmortem analysis over an entire data set. So you have one command to do that, that's called profile. And that we go through the entire data and extract a bunch of information. So as I said, we have very strong design constraints and implementation constraints. And I think, again, this is very important to understand that. Because if you don't, if we forget these constraints, the code will not make it into the repository because it will create problems for us later on. So it's mainly, the constraints are mainly about the scales of things. So we need to support around 5,000 MPI ranks. If you don't have experience, I'm sure it does not talk to you that much, but it's fairly big. So again, when you write code, you have to keep that in mind. And when we target to support about 1 million O2RV calls. So you don't have to actually run at that scale for your project. But again, when you write code, try to keep these constraints in mind. And that's usually what we have to do when we do our daily job anyway. So it's a good habit to develop. So yeah, it means you have to carefully choose your algorithms and your data structures. And that's also why you will see sometimes, if you wonder why the code is implemented the way it is today, that's usually why. It's because we have these scalability constraints in mind. So a few words about the validation tool. So the code ended up getting fairly big. I think today we are close to 20,000 lines of code between the profiler itself and the postmortem analysis tool. So there is actually a command in our infrastructure actually to help developers make sure that what they did does not break what is already there. So that's the validate command. And it's a separated command in infrastructure only because it goes way beyond unit testing. So if you are used to use GitHub, these days unit testing is very common to see, but unit testing has some limitations, and I won't develop why here, but it's a software engineering problem. And the validation infrastructure goes way beyond that. It's unit testing plus end-to-end testing. So it really tries to capture a lot of the assumptions, a lot of the expectations, and so on. It's not perfect. We are still developing it, but it's there. And I think it's actually very helpful. Usually it helps people see that they actually have problems and they did not really see it in the first place, only because it exercises things in a very specific way, which is not necessarily the way you do your testing when you do the development. And the rule is basically that if the validation passes and if the code does not contain anything that will create problems to maintain it, it just make it into the repository, no question asked. And if we discover issues later on, we improve the validation process, fix the problems, and we make sure that regressions will not happen in the future. So a few details about the creation of the profile. So there is 4 different types of information that are very important when we create that profile. Counts, and that's specific to the MPI operation, backtraces, location, and timings. And I will give a little more details about that in a moment. So for that, we have 5 different shell libraries. And again, it's because they are all very specialized. We don't have a single shell library that does it all. And having separate libraries really gives us an opportunity to do optimizations. And as I said before, there is a lot of complexity in the code to generate different versions of the shell libraries, so you can customize them based on your context. So for example, if you have a platform that is running low on memory, you have to do things differently if you want to get a profile at scale. And we have all these mechanisms directly implemented in the prototype, but again, you should not have to worry about it. It just explains why the code is the way it is right now. So for your project, I think you will have to use these 5 shell libraries, even if you will must certainly not use some of the data that are generating. But if you want to be able to use some of the commands, like the profile command I talked about, you will have to have the entire data set. So you will have to have to run your application with 5 shell libraries. And again, the README file has much more details about data, the format of the data, and so on. And I won't go through that right now, but we can talk about it later. So a little more details about some of the concepts I talked about. So first of all, the counts. So that's really part of the MPI standard. This is part of the API when you use the auto-LV operation. So please refer to the MPI standard. I know the MPI standard is sometimes different to understand, but that's really the best way to understand what counts are. And I won't try to duplicate what the MPI standard does here because we don't have that much time and we should always refer to the standard. Location. So location is really about the ranks, the communicating entities, where are they located in the platform. And that's data we try to gather because it's very useful to know for one specific node, are we using the entire network capacity or not. So it's a very useful information when we try to track down performance problems. So the backtrace, it really gives you a context about the application, how and when the auto-LV operation is called. And that's useful when we don't have access to the source code of the application, which in our case is most of the time. So it's basically a way to do some reverse engineering to understand how the application is calling these auto-LV operations. Late arrival and execution time. So you should not, I think, need that based on your subject, but I think it's important for you to understand what it is since it will be part of the data set. So when you have, and this is the example I have on the right-hand side, I have to move something here so I can see, here we go. So the green boxes, the green sections are the compute phases. The blue sections are the communication phases using auto-LV. There is a typo there, sorry about that. And as you can see, depending on what the ranks needs to do for the computation, it is very possible that one of the rank end up being slightly late compared to the others. And because of the way the semantic of the auto-LV operation, it means that the other rank would have to wait. So that's what we mean by late arrival, is one of few ranks actually have more work to do before entering the auto-LV operation, and they delay everybody. And as you can imagine, these delays actually drastically decrease the efficiency of the operation. So that's something we always look at, and that's why it's there. And for us, it's very important to understand these aspects. So that's what we mean by late arrival, and the execution time, it's very simple. It's the actual time it's spanning inside the auto-LV operation. So not considering the late arrival aspects. So we have some very specific mechanisms to capture these two metrics. It's not perfect. It's quite complicated. It's very quickly complicated. We are still working on it actually. But it's kind of out of the scope of this presentation. So if you have questions, we can see that later if you're curious, but let's move to the next one. So the postmortem analysis. So this time it's not about the creation of the profile, it's about the analysis of the data set you get once you executed all the shell arrays. So things to keep in mind. And this is why I choose Golang to implement the tool. Because of the constraints I presented before, it's very important to be careful about the API, the algorithms, the data structures we were using. The first version of the tool, I think a typical data set for an application that was using around 2000 or 12 calls was around 2 gigabytes of data. So when you write your algorithms, you have to be careful about how you deal with this huge data set. Fortunately, over time, we managed to decrease the size of the data set and make things more efficient. But this is still something you have to keep in mind because as we, as developers, move to more collective operation, this is potentially something that will appear here. And just to let you know, to run the postmortem analysis, depending on the scale, and I don't think it will be a problem for you because you will have only a limited number of nodes and ranks, but you may need a diff-cent system to run the postmortem analysis, or it will take a long time to go through the entire profile. So again, back to your project, I think you will have to worry about two commands mainly. The profile one, which we already talked about, and the web UI. And I will give details about these two in a moment. And I give here the location for the two commands. The default argument should be fine for what you have to deal with. So you don't need per se to understand all the arguments, what they mean, change them, play with them, whatever. You should not need to do that. And that's on purpose to make your life easier. I try to choose very carefully what these defaults are. Every time I click on that thing, it does the wrong thing. There we go. So a few concepts that are available in the postmortem analysis tool, and I think it's important for you to understand. So the first one is the concept of pattern. So R2RV is an MPI collective operation, which means all the entities that are communicating are involved at the same time and with basically the same semantics. However, for O2RV, that's the purpose of the V at the end of O2R. The amount of data that send and receive can differ from one rank to another. So of course it has to make sense, right? If you say that from one rank point of view, a certain amount of data is sent to another rank, the other rank has to expect to receive that amount of data. But the ranks are free. They are not, all the ranks are not sending the exact same amount of data or receiving. So, and it means we discovered over time that if you look at the developers of the application, the scientific simulations, and so on, we realized very quickly that very often O2RV is used beyond the initial intent, which is not really surprising, but beyond the initial intent, meaning they use O2RV just to do an exchange, not between all the ranks involved in the communication in the group, but only between a few ranks. So it's a very sparse communication, and this is actually most of the time also a source of performance bottleneck. So the patterns are really designed to capture that. So we have 4 different patterns that we can detect right now, and I won't talk about the details here, but the 4 patterns are one-to-one. So basically only a few ranks within the O2RV operation are communicating with a few other ranks. One-to-N, it's a few ranks are communicating with many other ranks. N-to-1, the other way around. So it's really about who is sending and who is receiving. And N-to-M is really what was the intent when the O2RV operation was introduced in the MPI standard is communication between most of the ranks that are involved in the operation. So the patterns is really a focus about how many ranks are actively involved in the communications within the operation. So now we have another concept, the concept of Heatmap. It's basically the same thing, but not focusing on which ranks are involved in the communication, but how much data is involved in the communication, is exchanged during the communication. And we have 2 types of heat map, and that will be a core concept for your work, these 2 things. So if you have questions after the presentation, feel free to speak up. But the heat map is really, we have 2 concepts. One is a rank-centric heat map, how much data each rank is sending or receiving. And the other one is a host-centric heat map, and that is how much data is sent, received per host. And as you can imagine, to understand, when we try to understand the performance bottlenecks, this type of information is extremely important. So the web UI, and again, that will be part of your work, so that's something that is important. So I am not a user interface designer, so the current implementation is what it is. It proved to be extremely useful to go through use data sets. And it's based on GNU-plot, so you will have to install GNU-plot. You will have also to understand GNU-plot down the road if you decide to use that technology. I personally use it because it's very flexible. The flexibility comes with a cost, which is complexity. It's not an easy tool to use. The scripts to write to generate your plots can be very quickly very complex. But some of the key features for the web UI, so it will automatically perform the postmortem analysis if some data is not there. If you start with a fresh data set, it will actually run the postmortem analysis on the entire data set. So in your case, it should be fun because your data set should not be that big. If you try to go beyond what is described in the topic of the subject, it may take a while before it comes up because it will go through the data. And if you have time, I will give you a demonstration about that. So you will see on the left-hand side, you will have a list of the calls. You can select them. And you can also see a summaries of the patterns. We don't have support for the heat map yet. And that is basically what the subject is about, is to include some of the heat map information in it. So as I said, the layout and the implementation still has limitations, but it's still evolving. We still make it better. It's still something we use very periodically. So we try to make it better as we go. So the task, Ophir, do you want to go through them or do you want me to do it?
So I suggest if we have time now before task, maybe let's go on the web GUI. I think it's important. And can you, how long it will, is it ready to show?
Yeah, it's ready.
Yeah, okay. So let's go over that and then let's go over the task. Just to demonstrate a little bit what we have.
So that's the web GUI for a very specific, very classic benchmark that we use to evaluate NPR performances, which is the OSU benchmark. It's executed on one single node. So it has limitation about the type of information it's displayed. And here it's a small screen, so it's not necessarily the best way to use it. It was designed to be used on a big screen, just because when you need to understand to investigate performance bottlenecks, it's better to have as much data as you can in one screen instead of having to click on multiple things. But on the left-hand side, you have all the calls. And on the right-hand side, you have the details. So you have one graph. It's basically the communication on each node per rank. So you have to go down. So it does auto scan and a lot of magic. We can talk about that later as you will look at the details. But basically, you see the counts and you see the communication, the amount of data, the number of ranks, the amount of data per rank, and so on. So the background color would differ if I was using multiple nodes. The background would be different for each node, so we can see very quickly if we have a problem with the node. But here it's on a single node, so you will not see it. But that gives you a feel about what the GUI is and the idea in the design. And the other point that is interesting to understand here is at the top, you have two tabs actually, cause, which is a default one, and patterns. So patterns is really the detection of the pattern I talked about. So here you can see it was 16,000 calls, O2RV calls, and all of them, that's what it says here, it's from call 0 to whatever the number here, is a dance, it's an M2M pattern. So all the ranks were involved and all the ranks were communicating with every other rank. So that's a very brief presentation. As I said, there is a lot of room for improvement, but that's the idea. So I will go back to the slide. Should we ask for any question at this point?
Yeah, sure. Anyone has any questions? Anything you want to mention? You can also use the chat if you want, if you feel easier, if it's easier. Okay, so let's. Can you move to the presentation? Okay. You know what? Let me also present. Let me open it because I want to toggle between that and the wiki.
Sure. So we have a question about the patterns on the chat. So what about the 424 text we saw in the pattern screen? So if I understand the question, it mainly, something I went over very quickly. So you saw the number of O2LV calls, around roughly 16,000. And it was a run where I was using 4 MPI ranks. So the 424 was really saying that all the 4 ranks were communicating with all the 4 other ranks, or every rank was communicating with every other rank in the O2LV operation. And that's really the way OSU is designed. It's a very dense communication when they use O2LV. That's what's in that's why it's an interesting benchmark. So that's really what it is. If you were using, for example, 1,000 ranks and all the ranks for OSU, actually you will see 1,000 to 1,000.
Okay, so what I believe is that you're all aware of our wiki. It's under HPC Advisor Council and Tassian.net. And here you will find detailed information about each task. It's all linked from the main website. That's it. So if we, I'm opening the wiki and I will toggle between. So the first task that we ask you is to understand what is MPI all-to-all-V. Okay. So just write a simple program to show the differences between the balance and unbalanced patterns. When we say balance, we mean that each node is sending the same amount of data. So first, all-to-all-V, to understand what it is, it means that each rank can send a different number of bytes to each other rank. Okay, so rank number 0 can send 5 bytes to rank number 2, 10 bytes to rank number 3, and so on. So it's vary, just the V. That's the V, right? So unbalanced pattern is when only 2 nodes are being sent the same amount of data. So we expect that to be more heavy on those 2 nodes, while other nodes are not doing much. While the balanced pattern, all the nodes are sending the same amount of data as the unbalanced, but just half of the cores or half the ranks per node are used. So what do we expect from the time? See the differences and send us the code. And this is more just to understand what are the problems. Okay, so this is fairly like basic, something basic, just to understand. Okay. Task 2, get to know the profiler. The profiler is under the Vallee account in the GitHub, and use the tag that we supplied just to make sure everyone is aligned in case we need to add, in case we need to change it because of a bug or something, we will inform you. But currently use this tag when you clone it. So what we suggest related to the way of working is that you clone it to your own, create your own GitHub account or working area, and just clone it to your area. And when we need to and make the changes over there, and when we need to review the changes, you can add Geoffroy to your clone area so he can review it, and later on the improvements can be pushed to the main profiler. So we are giving you the opportunity basically to improve this code, improve this profiler. So I don't know if I mean we are going to review it, of course, and look, but you know, the good codes will be pushed, can be pushed to the main repository. So task 2, it doesn't have to send anything, but just try that. So we ask you to run it with the GPOW and the WRF applications. The WRF application, I already put the 3 domain case on the website, so you can find it here, the link to download. So you can play around with it until we give you access to the real clusters, to the Niagara clusters for that. That's at the University of Toronto. The GPOW will probably will give you soon as well. And if you want to play around before those applications, you can also use OSU, All-to-All-V, or any other application that you're familiar that uses All-to-All-V calls. So this is nothing to submit here, but just to practice, make sure you can run the web UI and see the traces and understand the outputs. So with task number 3, what we ask you here is to identify the patterns, okay, and use the count. You have, so first you have all the data in different files in the outputs. It's there, okay. When we call what is a heavy profile, it's a pattern. Let's say, look at this pattern number 1. Rank 1 sent to rank 2, 10 bytes, 10 bytes, 0 bytes, 5, 7, 100. It is used in the MPI All-to-All-V calls in this example 3 times, and then number 2 is used only 1 time. So this first pattern is more heavier if we code, or the hair weight is used more. So this influence is more, will be more, will have more interface. Influence, sorry. So the task here is to display, to add to the web GUI, okay, this is a feature that we don't have. Let's say up to 10 most heavy patterns, so the patterns that are used more, okay, with different colors. I gave here some like example here, the different colors. So like 0 is a white color. If the number of bytes goes higher in a kind of a logarithmic scale, it gets a different color, from more or less from white to black. So once you see the patterns, you can imagine, or you can get a better understanding who is using it more heavier. So let's say I'm sending 1 megabyte to rank number 4. Rank number 0 is sending 1 megabyte to rank number 4, and just 1 byte to all the other ranks. We may want to have those 2 ranks close to each other in the application. So we can arrange the distribution or something like that. When we run it, we understand better how the application works. If we see, it will help us to visualize the All-to-All-V pattern. So in order to use it, we ask to use only 4 nodes with full PPN on Niagara cluster. Over there we have Skylake, Intel Skylake. There is 40 cores per node, so 160 a total of 160 cores, 160 ranks. So eventually here you'll need to, submit us the code, or basically give Geoffroy to review and show your work in the PowerPoint and the interview that we will have in the June timeframe. Okay. So task number 4, it's create a similar to task number 3, but just create a sum of patterns. What I mean by sum of patterns, just take each pattern, each of those patterns that we had, like this is one pattern, we had another pattern, we have another pattern, multiply it by its weight, okay, by the weight. So if pattern is used more, it will have more influence than another pattern that is used maybe only once. So just multiply it by the weight, and then and then apply the color to the cell. So let me know if you have questions here, but I think it's okay. It's okay. Okay. Then task number 5 is basically an extension to the colors. So instead of using only 8 colors here, just use 255 colors, 256 colors. And then I suggest here 3 distributions, how to, how many bytes per range. So one option would go with the just take the message length and divided it by 4K, and you take something like the minimum. So let's say 0 to each 0 to 4K, it's one color. So 0 to 4K is one color. Then 4K to 8K is second color. Color number 0, color number 1, color number 2. So each block of cells get each amount of bytes get the same color. Now that's one option, and you can choose it to see how this works. Another option is use more like a logarithmic distribution. So lower number of ranks, lower number of cells, like 0 to 10 gets one color, then 10 to 50 gets the second color, then 50 to 200 gets the third color. So as you go up in the scale, you don't need this too much of a distribution. And when you go down in the number of bytes, you need more colors on the low number of bytes, while less colors on the high number of bytes. Let's say between 1 megabyte and 2 megabytes, you don't need 100 colors. You can have one color to define 1 megabyte to 2 megabytes. But between 0 byte to let's say 1,000 bytes or 5K, you need maybe more colors. So I think it's also makes sense to maybe to investigate this area, or come up with another distribution of colors, maybe fixed, just make it some fixed or anything else. Show that that would maybe be better. So instead of seeing fixed, just 8 colors on the screen, you will see more granularity of the colors that will give you maybe different vision. Okay. Task number 6 is again somewhat generic, but find a way to map ranks to cores in a more balanced way. When I'm saying that, for example, use rank file or use any other way. So each node will send and receive, in this case, in the all-to-all V case, in a more balanced way. So what do we want from the profile? How are we going to use it? So let's say we found that only 2 nodes are being are using the Alt-V, and then the rest of the other two nodes are not using, which means that the time they will take to distribute all their data between the two nodes will be maybe double or maybe more than because the other nodes are not doing anything at the same time. So try to reshuffle the ranks based on their reshuffle the ranks based on their location in the node, and to see if that affects the application. Now, in our case, Wharf doesn't use so much Alt-V calls. It uses maybe around 1% in our test. So it won't make a significant, probably a significant change to the application time, but it will give you some idea or some things to think of for other applications. We may add another application here that we are looking for another input for in the GPOW with the GPOW application. So if we see that we have more Alt-V calls over there, we will use. I didn't want to introduce here another application for testing, but we might give it as an option. Just give you another application with more Alt-V calls, so you can see more differences, just to play around. Task 7 and 8 are generic tasks, and we look at that as a kind of a bonus task. So it's a kind of open task. Find a way to reduce the running time of the profiler. See, maybe you can run it in a better way. Understand the code, change the code, compare and show your results. And 8 is find ways to reduce the disk space. As this application puts a lot of data in the disk, on the storage, it may become heavy on the analysis and may become heavy on the user that wants to analyze his work. Okay, so eventually the raw data is good to have, but it's not easy to review. So we want to have more summaries, more visualizations, and more, let's say, easy ways to run it, so it won't generate. I mean, it may generate all the raw data, but eventually you want to review the bottom line. So try to find a way to reduce disk space. Currently, we're not handling that, for example. Okay, so I know it's a big challenge. That's why I wanted to give you a heads up and start this early as possible in a way. Submission. So as I mentioned, what I suggest is that you will clone your Git to your own Git area and work from there. We have here, I added here some examples from the output of the profiler. Sorry. This is an example of a directory after the run, many different files. Okay, that's the output. You will need to open the files that I mentioned here. You will have similar file names: Heatmap send counters, Alt-V Heatmap ranks, and I gave some examples here in this data. For example, this rank we have. So rank number 30 is sending zeros to everyone and just few 92,000 bytes, for example, to rank number 0, 1, 2, 3, 4, to rank 9, 10, 11, and 12 in this example. Okay, so you may see those things. You need to use the tools to parse it. You don't need to write parsers. You should have the tools to get that from the files. The files are written in a specific format. This is, for example, the generic number, then per rank, heatmap send. And this is per call, per rank. Okay, so all the files are text file. You can read those, and those gives you the patterns Geoffroy mentioned before, different patterns. For example, here 61 are sending out of 464, and in that pattern 181 are sending to 484. This is a slightly different pattern. So you're going to have all those files as an output when you run the application. Okay, that's the number of bytes per node. You can also use that to verify. So you can work on that in first on use your simple program that you wrote. You can write a small code that just send 5 calls and see what you get, see the output. Let me go back to the presentation. Okay, I think I mentioned everything. I mentioned everything. Any questions? See the chat. One question about the heat map. What does it mean that the diagonal grid points that mean that the rank is sending data to itself? Yeah, it's possible.
Yeah.
It's possible. You can see yeah, it's possible.
Yeah, it's actually a good point. We see that quite a bit in applications. When people develop their algorithms, they don't necessarily have in mind who is sending to itself. So you will see it quite periodically. And to be honest, it's also because most of the time the MPI implementations have optimizations for these use cases. So it's actually not getting on the network, it's just using a shared memory to do that. So application developers do not spend time avoiding it anymore.
Okay, good.
So
yeah.
maybe we can summarize why we selected those tasks. And I want to thank Sophia because he's the one who actually created the task. So why we selected these tasks? First of all, because MPI, if you're interested in HPC, you cannot avoid MPI. So we think it's a very good way to have a very practical, hands-on approach experience with MPI. And for finding application, understanding performance issues, trying to include visualization in the task you have to do, that is something we need to do all the time. As you get complex applications, large data sets, you cannot really avoid to have visualization techniques just because no human is able to go through gigabyte and gigabyte of data and extract information that is actually relevant. You have to have some visualization. So this project is really meant to have these aspects to expose you to those aspects. MPI, visualization, profiling, software engineering, hopefully. That's something that is very interesting to me personally. So that's why we selected this topic. It might seem to be overwhelming at first, but as you will start to look at the details, trick it down and everything, you will see that it makes sense. And we really believe it will be a good experience for you if you are interested in HPC. It will be very unique for sure.
Yes. So let me add also, last thing is that we try to give you a glimpse to the real life situations and real engineers, how they work, how do they try to, how they work in the industry. So eventually you're going to graduate and going to, get in one of the, hopefully one of the good companies in the industry, any company. And if you're going to work around HPC, you're going to see those problems when trying to make application run faster, and try to help you with that. So it gives you some glimpse to the industry, how things are working. So, Geoffroy, can you see the question from Luke Henry?
Yeah. I don't know. I really don't. We don't see MPI in place very often, so I did not try it. I would assume it is. I do not test it, so I will not claim it does.
Okay,
So the
good.
question for people who do not read the chat, does the profiler work when O2OV is used with MPI in place option? And yeah, as I said, I am not sure.
What is MPI in place? For people that doesn't know.
It's an option to attach a very specific semantic to send and receive phases.
And Geoffroy, I would expect that it would work, right? Because you're working at the profile level, so I would expect it would work, even though you haven't tested it.
Yeah.
Yeah. So.
I'm very careful, cautious here. That's why I said I don't know. I would expect it works because there is nothing in the implementation that would prevent it from working. But Rich is right. So by the way, the person who talked is Rich Graham, and so that's why I say I'm very cautious because I never tried it, but I would expect it would work.
Okay. So if anyone has any last questions, feel free to put it in the chat. If not, you're always welcome to use the Slack channel. Ping me, just write in the chat. If you have any questions, you can also email us. So to summarize, I want to thank Geoffroy for the good presentation here, and good luck for all the teams. And we'll see you next time in our next presentation. I forgot the date, but it's close to end of April, towards end of April. You can see everything on the agenda. I put all the details over there. Okay, so I will upload the recordings and send you the link to view it if anyone wants to view, and same in the presentation. We'll put it for you to use. Okay. April 26th, Luke Henry is helping me. Okay, so thanks everyone for joining, and see you next time.
Bye everyone.